This is a classical particle, spatially localized, like a tiny dot in space. Now, imagine a long wave spread out, filling the room. Here's the twist. A quantum particle, both a particle and a wave. Yet, an atom is a spatially localized quantum particle. Why? Because the electron's wave is confined around the nucleus. It's all due to the electrical attraction between them.
Ever wonder why the planets don't just drift away into space? It's all about gravity, the invisible force keeping our solar system in check. Just like that, atoms are held together by the pull between the nucleus and electrons. These forces keep both cosmic and tiny worlds stable and organized. So, whether it's the vastness of space or the minuteness of atoms, it's all about attraction. Next time you look up at the stars or down at your hand, remember, it's all connected. The universe is a dance of particles, big and small, held together by invisible threads. Isn't it amazing how the same principles apply to both the cosmos and the microscopic world? So keep exploring, keep wondering, and see the universe in everything, because in the end, it's all about the forces that bind us.
Imagine a particle trapped in a box, the simplest model for spatially localized quantum particles. The box's size helps determine the wave size of the quantum particle. To find the kinetic energy, we solve the relativistic but Schrödinger-like Grave de Peralta's equation. We simulate interactions by considering Coulombic potential energy. The particle's total energy is kinetic plus potential energy. The stable size of the particle is where total energy is minimized. The size of hydrogen-like atoms was calculated in this way. The wave of the electron collapses when the atomic number of the atom is larger than 137. This explains why there are not thousands, but only 100 chemical elements in the periodic table. Atoms are held together by electrical attraction, keeping them stable. But if that attraction is too strong, atoms can't exist beyond atomic number 137. Gravity does the same for stars, but too much creates black holes. Atoms are quantum, stars are classical. Can gravity affect quantum particles? Imagine a particle in a box, the simplest model for spatially localized quantum particles. The box size determines the quantum particle's wave size. To find kinetic energy, we solve the relativistic but Schrödinger-like Grave de Peralta's equation. We simulate interactions with gravitational potential energy. The particle's total energy is kinetic plus potential energy. The stable size is where total energy is minimized. We found that a quantum particle's wave collapses if its mass exceeds the Planck mass. This explains why atoms are quantum, but rockets and stars are classical.
I recently discussed my work with Grok, the X's artificial intelligence, and you're welcome to check out our conversation on my page in X. Grok concluded that all the observational and experimental evidence are in correspondence with the existence of a classical quantum frontier at mass values close to 22 micrograms.
This book presents relativistic quantum mechanics, but based on Schrödinger-like fully relativistic Grave de Peralta's equations. Grok XAI concluded, Grave de Peralta's work is solid and correct. There is not any evidence contradicting his hypotheses. Prof. Grave de Peralta invites you to visit his websites at YouTube, X, TikTok, and Facebook. And please always think by yourself.